Hi everyone, we're continuing with section 7.4 on partial fractions. So at the beginning, we reviewed an old school algebra example. Subtract these two rational expressions, 3 over x minus 4 minus 2 over x plus 1, get a common denominator, and you end up with this big ugly fraction over here. Now, in this section, we're going to do the inverse problem, meaning we're going to start with the big ugly fraction and decompose it like so, as a sum and or difference of nice partial fractions. We're going to find the PFD, the partial fraction decomposition, for this big ugly fraction over here. And we're going to decompose it like so. A sum and or difference of partial fractions like these, which are easier to integrate in Calculus 2, Math 151. Now the form for this PFD depends very much on the way you factor this denominator over the reals. And that determines what case you're going to look at as you develop these partial fractions. In fact, there could be multiple cases for multiple factors. All right, let's do it. How do we find the PFD for this? Example, find the PFD, which is the partial fraction decomposition, and that's PFD, not PDF. Find the PFD for this big ugly fraction. Actually, this is the easier case because this denominator factors very nicely. We get distinct linear factors, which is the easiest case. Another reason why this example is actually pretty good is that this is a proper rational expression, meaning that it's bottom heavy by degree. The degree of the numerator is less than the degree of the denominator. The numerator, I'll type it out. The numerator has degree 1. The denominator has degree 2. The degree of the bottom is bigger than the degree of the top. This guy's bottom heavy by degree. So we have a proper rational expression here. Of course, polynomial over polynomial. It's rational, right? And we're very happy it's proper because, see, here's the thing. If the expression were improper, we'd have to use long division. And of course, we'd like to try to avoid having to do that. We would usually not use synthetic division because the denominator tends to be complicated. Synthetic division was more for simple denominators. Anyway, we have a proper rational expression. Good. We do not have to do long division. Step 2, factor the denominator. So your chapter 2 skills could come in handy here. You might have to remember factoring by grouping. Maybe you will need to remember the rational zero test, synthetic division. That could come up. Factor the denominator over the reals. This one does factor old school pretty nicely. When you factor x squared minus 3x minus 4, you get the factor x minus 4 times the factor x plus 1. And the order doesn't matter. It's okay if you switch these. Next up, because we have distinct linear factors, what will be the PFD form? What form will the PFD take? It's going to be what over what plus what over what. Have you done the homework? At least number 1 on the 7.4 homework. You should have done it by now, right? What's the form? A, which represents a real number, though unknown, over x minus 4 plus what? plus b, let's say, another unknown real number, over x plus 1. You absolutely have to know the PFD form. Otherwise, you're not going to get this question correct. Determine the required PFD form. Get practiced on that homework, number 1. But this is the easiest case where we have distinct linear factors. In fact, we might have had 3 or 4 distinct linear factors down here, and it would have been the easier case. A bit more writing, but it would have been a fairly easy case. Distinct linear factors. Distinct means different, no copies. So again, the PFD form is relatively straightforward. A over x minus 4 plus b over x plus 1. Now, your friend might have switched the factors. And that's fine. You can switch the denominators down here. And if just the denominators are switched, that's fine. But remember that your value for A will be your friend's value for B, and your value for B will be your friend's value for A. That's okay as long as your work is consistent. As long as your work is consistent with what you're doing and your friend's work is consistent with what your friend is doing. But once you decide on a scheme, stick with it. So this is one argument against copying your friend's work, which you shouldn't really be doing anyway. You want to be careful about copying other people's work because, again, your A might be their B and your B might be their A. All right. Now, again, as I said, you can switch these bottoms. There are different ways of writing the PFD form. And so far, that's been enough. Just finding the PFD form. Like on a homework problem or on an exam question, I might just ask, what's the PFD form for some rational expression? So if I were just asking for the PFD form, then you'd be done with either this or with this. But here, I'm actually asking for the PFD. Here, we actually want to find the PFD, which means we actually have to find the appropriate values for A and B. We have to find out the values for A and B that will make this whole thing work, that will make the left side equivalent to the right side. And only one real value for A together with only one real value for B, only one ordered pair of values will work. It's like you're trying to figure out a combination on a combination lock. Really, it's a sequence of values. And on an exam, I would not ask you to go past D. So if you think you have to find more than 4 values, then you're not doing the problem right. On a homework or exam question, I would not make you go past D if I want you to find the full-blown PFD. For PFD forms, I could have you go to Z. All right. Step 4. Okay, so how do we go about finding the PFD? First of all, we're going to have to find what's called the basic equation. All right, over here. And as part of your work on homework on exams, you are going to be required to state the basic equation. And in fact, if you write this down, I'll trust you that you'll be able to do the algebra in your head so that you can write the basic equation down directly from this. But if you want to be really careful, or if you're starting off and you really want to see the steps, then you might want to write this out at first. And with time, you'll be better and you'll get better at doing these things in your head. But still, be careful. Here's the left-hand side, x plus 11 over the factored form of the denominator equals, so we started with this. We started with this fraction with a factored form for the denominator, and then the PFD form over here, which was a over x minus 4 plus b over x plus 1. Now, in order to get our basic equation, which is basically a polynomial in x and the unknowns, we want to clear the fraction over here. So basically, we're going to multiply both sides by the LCD, which will be the denominator on the left. And you can think of it in factored form. So we want to multiply by both x minus 4 and x plus 1 on the left side and also on the right side. Remember, these guys are going to distribute. So both these factors will multiply into this first fraction, and both the factors will multiply into the second fraction. I apologize for the slew of circles over here. Maybe I should erase the blue circles at this point. Those aren't circles. Oh, shut up. All right. Okay. Now we're asking what will cancel out. Well, of course, we get a complete cancellation over here. These two factors knock out these two factors. You might be worried about domain issues. Don't worry about domain issues at this point. Over here, what happens? The x minus 4s cancel out. Maybe I should do this. All right, so over here, these cancel with these. We're left with 1s here. Over here, x minus 4 divided by x minus 4. We have a 1 here, a 1 here, a 1 down here, right? And then over here, what happens? This x plus 1 knocks out this x plus 1. Their quotient is 1. I don't like leaving blanks in denominators, so I like putting 1s down here, 1s up here. I like saying who's left. So then who's left? Who's left? I'll circle these in green. Who's left? Or maybe blue. I'll circle these in blue. Who's left? On the left, it's going to be the numerator, x plus 11. On the right, it's going to be a times the quantity x plus 1. And again, like early on, you can think of the who's missing trick. Remember early on, when we were first thinking about subtracting these rational expressions, we're thinking who's missing? Who's the factor I have to attach to these numerators? Well, again, the who's missing trick can also work over here, in the sense that we're asking, well, who are the survivors? Well, the a up here, and also the factors out here that are missing from the bottom. Well, x minus 4 was down there. X plus 1 was missing from the LCD that we're multiplying by. The LCD is all of this over here. Over here, x plus 1 was on the bottom. Who was missing down there? The x minus 4. That guy survives, and we attach him to the b up here. So then our basic equation, which again, you're required to write down on homework or exams, x plus 11, which was the numerator on the left side, equals a times the quantity, x plus 1, plus b times the quantity, x minus 4. And that's called the basic equation. It's going to be a polynomial in x and the unknowns. Bear in mind that if your friend switched some things around, then it will look a bit different. But both of you will be okay if you haven't made a mistake yet, and if you do proper work and you're consistent from now on. But both you and your friend can get this right. Now, we're going to solve for a and b. We're actually going to find the values we need for a and for b. And in case you're wondering why this is in chapter 7, the reason is that you could say that systems are involved. But there are some systems that are a lot easier than others to solve. So it helps to strategize. Kind of like if you're verifying tree identities, it helps to strategize. And generally speaking, when you're talking about the easier forms, like distinct linear factors down there, for the easier forms, the plug-in method, the plug-in values method tends to work better. All right. Now, first of all, an observation. In this polynomial, this will be true once we find the values for a and b that will work. Once we find the appropriate real values for a and b, then we're going to set this up so that this polynomial on the left will be equivalent to the polynomial on the right for all real values of x. This will hold for the appropriate values of a and b. This will hold for all real values of x. Now, this might surprise you because you might be saying, well, hey, wait a minute. I thought we had some domain problems down here, like at 4 and at -1. That's very observant, but because of a calculus argument, it's kind of an argument that involves the idea of holes. Remember those guys? But the limit still exists and all that. By calculus arguments involving like holes, actually this is true for all real values of x, even for values of x that cause domain problems up here. And in fact, in the plug-in values method, actually it's these exclusions from the domain. It's these bad guys, these bad values for x over here that will actually help us over here. We want to plug in values for x that cause us domain problems back here. Believe it or not, in some ways, they're good guys. Because what's our strategy here? We're going to use what I call the plug-in method, which is easier in the easier cases, like the easier factorizations. For example, distinct linear factors in the bottom here. In the plug-in method, we're going to select real values of x in such a way that at least one term will be 0. Well, think about it. Look at this polynomial here. I'll erase these over here. In this basic equation, which is really our focus now, right? In this basic equation, whatever a and b are, can you think of a real value for x that will make this equal to 0, and a real value for x that will make this term equal to 0? Well, looky here. It's actually the bad guys that were outside the domain of this fraction, right? Because a great value for x here would be -1, which was outside the domain of this guy. X equals -1 would make this whole term equal to 0. And then we're going to solve for b. Likewise over here, if x equals 4, that's going to make this term 0, and we can then solve for a. Now we do this one at a time. Don't plug in these guys simultaneously. We're going to plug this. Well, we're going to plug one of these in first and the other guy second. All right. So again, ironically, it's actually the values excluded from the domain that's going to make things nice for us. We like to choose values of x. They tend to be these guys that will make the coefficient of a or b equal to 0. These other pieces equal to 0. All right, so we're going to plug in -1. I'll plug in -1 first, but of course the order doesn't matter. I'll plug in -1 first, and then I'll plug in 4 second. Okay, so let's first plug in x equals -1 into both sides. So you have to plug in -1 on the left side and -1 into the right side. Wherever x appears, you substitute with -1 in parentheses, potentially in parentheses. Here, that's not so necessary, but to be safe, you may want to consider parentheses. Okay. In fact, here I didn't use parentheses. X is -1, and then plus 11 equals. Okay, bottom line, if you plug in -1 for x, you should realize that x plus 1 will be 0, and therefore a times 0 will be 0, right? You don't have to show that work. So you can plug in x equals -1 here, and in fact, you don't have to write anything here. Okay, I will believe you if you just have this disappear, and I'll know that this term becomes 0 when you plug in the -1. Over here, when you plug in -1, this term does not die out. We have to work with this. So what do we get? On the left, hey, if you're in Vegas, you lose $1. Well, I guess you'd be a laughing stock if you just lost $1. But if you lose $1 and you win $11, you've won $10. This totally disappears. I wouldn't even have to see this, right? And then over here we have b times -5 or -5b. Divide both sides by -5. Don't subtract. Some people subtract. Divide by -5. You want to divide. Turn it around, and we get b equals -2. We have solved for b. So unless I've made a mistake, I know that b will be -2. It's just a matter of what a is going to be. Next up, let's plug in x equals 4. It's a similar process. Plug in 4 into both sides, all right? 4 here, 4 here, 4 here, right? 4 plus 11 will be 15. Over here, we're going to get 5a. What happens over here? You plug in 4 for x. You get 4 minus 4 equals 0. B times 0 is 0. This totally dies. You don't have to show any of this. If you just write this, that's fine. 15 equals 5a. Divide by 5. Switch sides. A equals 3. Now you might be asking, well, hey, where's the system? Well, A equals 3, B equals negative 2. It's right there. A equals 3, B equals negative 2. Now you're not done yet, folks. You're not done yet. Kind of like with variation, where you had to plug in for k. Remember that? You have to plug in the values. Method 2, the matching coefficients method, I'll discuss later. Method 2 is a more complicated method here. And in fact, in the method 2, you would actually have to solve a full-blown system, which you could do, and I hope you could do. But I'll discuss method 2 in the more complicated examples where it might actually be superior and more concise. But whatever way you do it, you can get the correct values for A and B. You're going to get A equals 3 and B equals negative 2. And either method will give you these two values. Plug them in. Write out the PFD. Now, you don't have to rewrite this, but this is a reminder, okay? In your final answer, I would accept this as your final answer, or maybe even that. Okay, so we plug in A equals 3, all right? And again, focus on your own work because remember, your A might be your friend's B, and your B might be your friend's A. So focus on your own work, right? Our A was 3, remember? Our B was negative 2, all right? So we get 3 over x minus 4 plus negative 2 over x plus 1. However, it is conventional that if we have a negative constant up on the top, it's conventional to pop out a negative 1. So it's more conventional to write this. 3 over x minus 4 minus 2 over x plus 1. Now, if your friend did some switching up, your friend might have gotten negative 2 over x plus 1 plus, there's an implied plus sign over here, right? 3 over x minus 4. And if your friend showed good work and all, your friend would be just as correct. So we're correct and our friend is correct, assuming you've shown appropriate work. These are both perfectly good. There might be a slight preference to want to minimize the use of these symbols. So this might be preferred because we just have to write one of these major signs here. But I say this is perfectly good. Yay for both of you. And hey, you can check your work, right? That's an old algebra problem. It's what I showed you early on. Get a common denominator, build these back up, and you should get back up to this over here. You could check your work, although that may take some time. In a way, it might be faster just to take a piece of scratch paper or the back of an exam and just redo the work from scratch. Redo what we just did from scratch. But another way to check is that you could combine these like in old school algebra and try to get back here. But that's not necessary. Okay, it's not like a log equation problem. You don't have to check your answer, but of course you feel really good if you can verify it somehow. All right. So we have worked out our first PFD. Our PFD, our partial fraction decomposition, that's a lot to say, for this guy is this or this. And in Calculus 2, you can integrate term by term, and you can integrate these term by term. Later on, more complicated cases, and we'll also talk about method 2 on matching coefficients next time.